All right, now we're working on more functions, constructing them, determining if they're linear or nonlinear, and doing some qualitative graphs. We're on pages 16 through 18 today. We have number 1, are the following functions linear? Most of you remember this. If you don't remember this, I want you to write these things down. First of all, x and y both have to have exponents of 1. Okay, they have to have really no exponents there because we know that's an exponent of 1. All right, and x and y both can't be multiplied together. You can't have x times y. That's written like this, x, y. Can't have that. There has to be some kind of sign in between them. And lastly, which is a bunch of things here, you can't have x and y in denominators, exponents, or radicals, meaning we can't have 1 over x, something like that. You can't have an exponent, so we have, 2 to the x, can't have that. And you can't have a radical over a variable. You can have a radical, you can have a fraction, you can have an exponent, as long as they're not variables in them, like that. Okay, so let's do this one. Number 1A, I'll call it. Is that one linear or not linear? Looks like it satisfies everything. Exponents are good. They don't get multiplied together, and there's no x in the exponents and all that stuff. We're good. So this is yes. Okay. If it's no, we're going to circle the reason why it's not linear. Like, for example, the second one here is no. Do you know why? It's that exponent right there. The next one might be hard to tell, but let's distribute and see what we get. We have y equals, 3 times x is 3x, and 3 times negative 4 is negative 12. That's linear. We're good. And the last one, again, y squared. Can't have a squared there on your variables, so this is a no. All right, number 2, a bacteria colony triples its mass every hour. Does this situation model a linear function? Linear. Well, is it linear? Well, it might be hard for you to tell. Maybe you just know right off the bat. But what we can do is just make a quick table with an x and y. So x can stand for time, right? Time in hours. That says hours there, in case you're curious. My handwriting's a little weird. Hours. And then y is standing for the mass, right? So we don't know really what it started with, but we could start with anything. How about at time 0 it started off with a 1? We don't know. Whatever. Okay? Well then every hour it's tripling, right? So if we go up 1 hour, what's triple 1? That's 3 times 1. That's 3. Let's go to hour 2. Well, it's going to triple again. So what's 3 times 3? 9. Let's do one more. At hour 3, it's going to triple again. So 9 times 3 is 27. And of course, linear will have the same what? It will have the same slope. So let's check the slope here. All right. Change in y, getting bigger by 2. Change in x, getting bigger by 1. So the slope there is 2 over 1. Here we have getting bigger by 6, getting bigger by 1. Are they equal? No. So this is not linear. If you picture a graph of it, you don't have to write this down unless you want to. If you picture a graph of it, it's going to get exponentially bigger. It's an exponential function. It's going to slowly get bigger, but then eventually increase quickly. It looks like an exponential function, and it's actually written something like this. Y equals triples, so triples, and that's the x in the exponent, which makes it not linear. All right, does this table form a linear function? Well, we just did the table, right? We have to see if it has the same slope, right, for linear. Well, let's see. This one is smaller by 4. This one's getting bigger by 1. This one gets smaller by 2 and still bigger by 1. Does 4 over 1, does this one equal the second one? Negative 4. Does that equal that? Nope. Not linear. The graph is pretty easy. You can tell it's not in a straight line here, so that would be no. And page 17. All right, we are constructing some functions, which means we need, notice you see this a lot in this class. This is very, very important. Okay, so to find this, we need to find m and b. So m is going to be the change in y over the change in x. So the change in y is 3, positive 3, and the change in x, that's a positive 1. We're getting bigger by 1. So we have the slope equaling 3 over 1, or just 3. So slope is 3, and the y-intercept when x equals 0. If you don't have it in your table, you'll need to find it. But for now, we have it in the table. When x is 0, y is 5. So b equals 5. So this equation or function is y equals 3x plus 5. mx plus b. Okay. Number 2. Write an equation of this linear function. So we have slope. Well, it's the rise over the run, which is the change in y over change in x. It's the same thing. From a graph, look for the rise and the run. Pick any 2 points that you can see and find the rise over the run. I'm going to pick these 2. Maybe you picked different points. Okay? Here I'm going up 1 and right 2. Oops. 1. Rise over run. Rise first. Rise goes on the top. Okay, so that's our slope. 1/2. And the b is when x equals 0. What does y equal? Right here. It's 3. 1, 2, 3. Yep. B equals 3. We'll point to it. So there we have it. Y equals mx plus b. M is 1/2. Don't forget your x. All right, let's do another one. It costs $100 to join a health club and $50 per month to use the facility. So we have $100 to join, and it's $50 per month. This right here is a key word. You need to know that. What value represents the rate of change and initial amount? So let's do the 2. We want rate of change, and then we want down here initial. All right. Well, the rate of change, we can find it from words with that key word per. Per is a key word. Per, each, every. If it says any of those things or something that means any of those words, that's your rate of change. So our rate of change is 50. Therefore, our initial amount is 100. And that should make sense to you. If it costs 100 to join, isn't that an initial amount, the beginning amount, initial? So those are the answers for number 3. Number 4 wants me to write an equation to model the health club fees in question 3. So it wants me to write an equation for this stuff. Well, we know the M is 50. The slope is 50, I should say, and the y-intercept is 100. So if they want us to use C and M, I'll go ahead and use that. Let me write it like this first. And of course, this M is not the same as this M, okay? Just to make sure you know that, okay? But if I'm going to write it in slope-intercept form, let me do that first, where you know your M is the rate, which is 50, and the y-intercept is the V, which is 100. Now let's write it using their letters. They want us to use M and C. So C is the cost. Well, the cost is what it equals in the end. So that's this one. The cost is $50 per month, right? And it said it right here, $50 per month. That's why the 50 goes with the M and then plus the 100. Okay, and the last page for this one is going to be page 18, where we're doing qualitative graphs. All right, we're going to match the different line segments with the description. So let's look at these for a second. A is this line here. As you can see, as time goes on, speed is increasing. Do you see any other increases on this graph? I have another increase right here. Okay, there are 2 increases. That's the only 2 I see that increase. Which one increases more quickly, A or D? I would say A. So if we look down here at our options, we have constant rate, we have slowing down, speeding up, slowing down, speeding up. So we want to look at the 2 speeding up, right? Because we're going uphill. So one does more quickly, one does more gradually. So as you can see, I want the one that speeds up more quickly. And I'll make it a little smaller and turn it here. It's going to go on A, right? That's more quickly than this one. Oh, you can't read that. Okay, there we go. So if we're going to match these up, I'm going to draw lines to the A and then the D. So A is the one that speeds up more quickly. So that A goes to number 3. You know what we could also do is maybe just write the number on the graph. So this, and so instead of doing these, let's move this out of the way. Maybe that's less confusing. 3 is this one. It speeds up more quickly, and of course, let's see, D goes to number 5, which speeds up gradually, right? That's 3 and 5. Those are our speeding up sections. All right, now let's look at some slowing down sections. If you see 2 that slow down, get slower, get less speed, that would be a downhill slope. That would be C and E. Which one slows down more quickly? Which one slows down quickly? That would be number 4, okay? That's C, right? C goes with number 4. I'm going to put a 4 next to the C. Therefore, the other one that slows down, which is number 2, is going to be E. So E goes with number 2. I'll put it here as well. All right, speeds down more gradually. So then we have B, which does absolutely nothing in terms of speeding up or slowing down. So it travels at a constant rate. So that would be B. So always pay attention to your axes, the speed and time, and figure out what it's doing, right? As it's going up, speed is increasing. As the time is going up, it's getting further along in time, and so forth. Tom leaves the school at 3 o'clock. He walks to the park, where he plays for 30 minutes. Tom realizes that he forgot his backpack and goes back to school. He then hurries back home, which is past the park, and Tom walks at a constant rate. So when he walks, it's a constant rate. Let's see. So what did he do first? He's leaving school, he walks to the park. So he's walking at a constant rate is what they said, which means a straight line, constant slope. Move this out of the way. So we have to see the graph here. We have time and distance from school. So if he's walking to the park from the school, obviously the distance is getting further from the school. So we're going to walk some amount. It's not going to be perfect, okay? And maybe I'll make it a little less steep even, just because he's walking. It's not very quick, okay? So there he goes. That was his walking to the park. And I'm color coding if you can see this. This is a red. All right, and then he plays for 30 minutes, and I'm not going to do time on this really, but if he's playing for 30 minutes, does his distance from the school get further or less? No, his distance is going to stay the same, so his distance doesn't change, so zero change in distance would be a zero slope, okay, for however many minutes. All right, what happens next? Well, then he realizes he forgot his backpack, okay? And he goes back to school. Okay, it doesn't say that he walked fast or anything, so I'm going to say that that is going to be the same slope as the other one, except this time he's going back to school. So his distance from school is getting less. That doesn't look the same as the red. Let me change it, make it a little better. It doesn't really matter so much. That's good. It's closer to the red. Okay. Then the last part is going to be, let me change my color here. Then he hurries back home, which is past the park, which means it's further from the school than the park was. And the park is the green spot on the graph. So if I want to hurry, means I'm going to go faster, means my slope's going to be bigger, and I'm going past. Let me make that a little straighter. It's going to be past where the park was. No one's to say how far that line goes as long as it goes above the green line. Okay, that is all for that.